Hey everybody, this is Mr. Mazzoro, and today I want to start talking to you about the chemistry of ocean water. It's not going to be a typical chemistry course. We're not really going to talk about the periodic table, and we're not really going to talk about chemical reactions. What I really want to talk to you about today is start talking to you about the idea of how water as a molecule actually affects the life on Earth and the life in the ocean. So we're going to start talking about what is water the molecule and why is water on Earth unique? Why are we the only planet with life on it? And what does that have to do with water? And then we're going to talk about what water molecules actually do in solution. And the reason we're going to talk about what molecules actually do in solution is because that has directly to do with a lot of the way life is in the ocean. So let's begin with what makes water on Earth unique. So this is Earth. You're probably familiar with it. It's a big ball. It's blue, and it's blue in part because of water. And it's really important to understand that what makes water on Earth unique is not that there is water on Earth. There's water in tons of places in the universe. There's water on comets. There's water on moons. There's gaseous water or steam on Venus. There's solid water on Mars. So what's the deal with water on Earth? Why do we care so much about water on Earth? Well, it's not so much that we're the only planet with water. It's the fact that we're the only planet with liquid water. That's what makes water on Earth unique. Now, when we look for life on other planets, we're not actually looking for aliens. We're not looking for little green guys waving back at us. As far as we know, all life on Earth requires water. And so we don't have to look for aliens. We just have to look for other places in the universe that have liquid water. And as far as we know, we're the only planet presently that has liquid water. There may have been liquid water on other planets at some point, but we're the only planet that has liquid water presently, and therefore we're the only planet with life that we know about. So if we're going to talk about the liquid water on Earth, we have to talk about where it is. By far and away, most of that liquid water on Earth is salt water in the oceans. About 3% of all the liquid water on Earth is fresh, and 97% is salt. And then even that fresh water, most of it isn't in the lakes and swamps and rivers on the surface. That's only a fraction of 1% of that fresh water. The vast majority of liquid water on Earth is salt water in the oceans. So what's water doing in the oceans on a chemical or molecular basis? Well, here you go. Here's a water molecule, 1 oxygen atom and 2 hydrogen atoms. Now, water molecules don't share electrons evenly. Electrons, remember, are those negative things that wing around atoms and molecules really, really fast. The oxygen atoms in water molecules are much, much larger than the hydrogen atoms. And as a result, those negative electrons in a water molecule spend more time around the oxygen atom than they do the hydrogen atom. Because the negative electrons spend more time around the oxygen atom than the hydrogen atoms, that makes the oxygen atom slightly negative. And vice versa, because there's less electrons or negative electrons spending time around hydrogen, that makes the hydrogen atoms slightly positive. So water, the oxygen bound to 2 hydrogens, actually is polar. It has a negative end and a positive end. This is important because when you get 2 water molecules next to each other, they both have negative ends and positive ends, and those negative ends and positive ends start sticking to each other like magnets. And that sticking is called a hydrogen bond. Water molecules in solution are forming and breaking these attractive bonds all the times, millions and millions and millions of times a second. Hydrogen bonds are forming and they're breaking. Why do we care about hydrogen bondings when all we really care about is fish in the ocean? It's because those hydrogen bondings create a lot of really important properties of water that life on Earth and life in the oceans has come to depend on. So let's talk about what those properties are. The first property we have to talk about is how water absorbs heat. The way any molecule, water included, absorbs heat energy is through vibrating. The more heat energy a molecule has, the faster it moves in solution or in a solid. And like I said, the slower the water molecules or any molecule is moving, the less heat energy they would have, or the cooler they would be. The thing with water is that, like I said, water can hydrogen bond. And those hydrogen bonds stop water from moving around as much as a lot of other substances that don't hydrogen bond. Things like wood or rubber or aluminum or concrete or sand or air or glass or steel. As a result, it takes a lot more energy to get water molecules moving than it does all these other substances. It would take a lot more energy to cause water molecules to heat up, move, than it would these other substances. This idea that it takes more energy to heat up water, that's called heat capacity. Water is said to have a very high heat capacity. It takes a lot of energy to heat up water. Or even simpler terms, water heats up or cools down very slow. It's an insulator. But why do we care about this? Well, we care about this because most of the life in the ocean, fish and snails and crabs and plankton and bacteria, all of this life is cold-blooded. The reason it's cold-blooded is because they don't have to worry about regulating their body's temperature. They don't have to worry about putting energy into their body to keep themselves warm or cool. They can just figure that water's high heat capacity is going to keep the water temperature around them relatively stable. Most of the life in the oceans is cold-blooded because of water's high heat capacity. The exception to that are the mammals in the oceans, the whales and the dolphins. They're warm-blooded, that's true. But keep in mind, they weren't always in the oceans. They were once on land and reverse evolved back into the oceans. When they were on land, they had to be warm-blooded and evolved to be warm-blooded, mostly because air has a much lower heat capacity than water. And when they reverse evolved back, they just kind of kept that. So water's high heat capacity, water's ability to hydrogen bond causes it to have a high heat capacity, which causes most life on Earth to be cold-blooded, or life in the oceans to be cold-blooded. The other reason why water's heat capacity is very important is because that allows water, specifically the oceans, to regulate the Earth's temperature. The oceans will heat up cool air above them in the poles, and they'll also cool down hot air above them on the equator. And this keeps the air above the oceans at a relatively stable temperature, just like the oceans themselves. You might have probably noticed this. If you go to the beach during the summer, the beach is always colder, a couple of degrees colder than it is farther inland. And that's because the oceans take a lot of energy to heat up. They heat up a lot slower than air, and they're actually cooling down the air around them. What's even more wacky, and you probably haven't noticed this because you don't go to the beach during the winter, but if you go to the beach during the winter, then the oceans are actually warmer than the air around them, and they're actually heating up the air around them. Water's ability to hydrogen bond causes it to have a high heat capacity, heat up or cool down very, very slowly, which allows life in the oceans to be cold-blooded, and it also allows Earth's temperature to be regulated. The next property that hydrogen bond actually affects with water is how thick or thin water is. The measurement of how thick or thin water is called viscosity. Viscosity is any liquid's tendency to resist flowing. Thick liquids are said to have a high viscosity, things like molasses and honey and syrup. Thin liquids are said to have a low viscosity, things like mercury and nail polish remover and gasoline. Water can hydrogen bond, which means when water molecules try to flow past each other, they form these hydrogen bonds and start sticking to each other. And that causes water in liquid to have a slightly high viscosity, not as high as honey and molasses, and not as high as syrup, but high enough. This means that most of the smaller things in the ocean can't overcome that viscosity. To them, water is just too thick. They can't swim through it. And as a result, most of the smaller life in the ocean is plankton. That means instead of swim, they float or drift. Plankton is any organism that floats or drifts. The reason they're floating and drifting is because they're small and water has a relatively high viscosity, and as a result, they can't swim through water. To them, it'd be like swimming through concrete. Larger things in the oceans, like larger fish, obviously can swim through the oceans because, like I said, water has a slightly high viscosity due to hydrogen bonding. It's not super duper thick like mercury or molasses. Water's high viscosity is caused by hydrogen bonding, which causes there to be plankton in the ocean, most small marine organisms in the ocean, to float or drift. Lastly, hydrogen bonding causes ice to float, and this is really unusual. It's very unusual that a solid would actually float on its own liquid, that solid water or ice floats on liquid water. Most other substances in the universe, when they turn to solid, they get more dense and they would sink. What's even more crazy is that it's true what I said in the last lesson when I was talking about currents, that warm water is less dense than cold water. If you look at this area of water, there's a lot less mass of water molecules in the warm water than in the cold water. So warm water would float on cold water. But remember what I said about temperature. The colder you make anything, water included, the slower its molecules begin to vibrate. And in water's case, the more chance they have to form hydrogen bonds and not break them. As a result of forming hydrogen bonds and not breaking them, water will actually begin to form a lot of hydrogen bonds around 4 degrees Celsius. And when it forms a lot of hydrogen bonds around 4 degrees Celsius, it begins to float. So it's because those last 4 degrees that you get lots and lots of hydrogen bonding that water molecules will actually spread out, and they'll actually cause water to float, or solid water or ice to be less dense than liquid water. This is really important because keep in mind, if ice is floating, if cold solid water is floating where the hotter water is, it's going to start melting. If water was like every other molecule on Earth, and when it turned to a solid, it just sunk down, that would mean that it would sink to where the colder water was, and it would melt a lot slower. And in the meantime, more water would turn to ice and sink, and more water would turn to ice and sink, and more water would turn to ice and sink, and eventually the oceans would freeze over. It's because water floats, because ice floats on solid water in those last 4 degrees, that the oceans are liquid water, that they're not solid water. And it's because ice is floating, even though we just kind of take that for granted as truth. In some ways, it's because of that that you can attribute all life on Earth, the fact that we have liquid water on Earth. So, what makes water on Earth unique? Again, it's the idea that we are the only planet with liquid water. Not we're the only planet with water, we're the only planet with liquid water. And that liquid water on Earth has a positive end and a negative end, which means that in solution, water sticks to itself like magnets. This causes water to heat up and cool down very slowly. That's called heat capacity. This causes water to be very, very thick, or not very, very thick, but thick enough, and that's called viscosity. And this causes water in those last 4 degrees Celsius to start expanding and spreading out, and that causes ice to float on liquid water. The fact that water has a high heat capacity means that most organisms in the ocean are cold-blooded, and it also means that water can regulate the Earth's temperature. The fact that hydrogen bonding causes water's high viscosity means that most small microscopic things in the ocean float or drift. They're plankton. They don't swim. And lastly, the fact that hydrogen bonding causes solid water to float on its liquid counterpart means that that solid water or cold water is going to melt, and it allows the oceans not to freeze over and for life on Earth to begin. So that's it. That's our first lesson with the chemical properties of water and how those chemical properties actually affect life in the ocean. And it has to do with the idea that there's liquid water and the idea that water can hydrogen bond.